So Shashank, whenever you're ready.
Okay, yeah. Welcome all to this talk in the Theories Matter seminar series. This particular talk is also part of the IEEE KYP series organized by the IEEE Kharagpur Young Professional Group. It's a pleasure to have Birenjith give a talk today on the theory of simulators for COVID-19. Birenjith received his B.Tech from the College of Engineering Trivandrum in 2002 and his master's and PhD from IISc Bangalore in 2008 and 2017 respectively. In 2012, he worked as an intern in NetApp Bangalore, and currently he's a faculty member at the Govt Engineering College, Barton Hill in the Department of ECE. He has worked as a member of the team constituted by Kerala State Disaster Management Authority to model COVID-19 epidemic for the state of Kerala. And they also have a simulator called COVID Sim, which he's going to be talking about today. His areas of interest are codes for distributed storage, wireless communication, and coding schemes for 5G and IoT. So I hand it over to Birenjith. We're looking forward to this talk.
Okay, thanks Shashank and Amit for inviting me for this lecture. It's a pleasure to deliver a lecture on COVID, which is not my area of expertise, but I have recently learned a bit about that. So, two remarks at the outset. The first one is an apologetic one. So this talk is not going to present any new theoretical contribution which we have made. So if someone has joined this talk with that, keeping that in mind, it will be slightly disappointing. Second remark is that this talk is not going to be about the actual numbers of COVID-19 infections or the projections in India or anything of that sort, but it only talks about the theory behind making such models and projections. Okay, so let me start with some huge list of acknowledgement, because as I already pointed out, I learned about this area recently. Very long, brief interactions with a huge number of people helped me study a bit on this epidemic modeling. Particularly the simulator which we built was in collaboration with Deepak from IIT Palakkad, Sriram from Amazon Palo Alto, Sajid from Qburst Technologies, Arun from United Nations, and Kiran from Google San Francisco. Okay, so the outline of this lecture is as listed here. So we'll talk about standard available models that are used for making epidemic projections. The first one is the deterministic compartmental model, which can be used for modeling the time evolution of infections caused by an epidemic. The second one is metapopulation model, which can help you study the evolution in terms of space as well as time. And the third one is stochastic agent-based model, which comes under a slightly different category. And finally, we'll end this talk giving pointers to some example simulators that are created within India. Okay, so as we all know, the virus SARS-CoV-2 has infected a sizable population of the world, and it has shattered lives at individualistic level and at society as a whole. And there are various factors why this has infected a large number of people, some of which are listed here. Usually the viruses, the receptors which accepts viruses in human body, especially particularly the respiratory viruses, either the receptors are present in the upper respiratory part or in the lower respiratory part. If the receptors in the upper respiratory part, the severity may be less, whereas the disease transmits a lot. And if it is a lower respiratory part, the severity may be harsh, but it transmits less. This is a unique, SARS-CoV-2 is unique in the sense that it has receptors in both upper respiratory and lower respiratory parts, making it both severe as well as it contagious alone. And unlike many other corona-like viruses, it has a fragile covering. That means it can break easily and stick on to the receptor quite quickly. While the covering is fragile, the internal RNA is quite robust. It's one of the longest known RNA sequence, a virus having the longest known RNA sequence. And there are many other factors which makes it very a powerful virus in terms of its severity and the rate of infection. So because it has affected us all, it becomes important to ask certain questions. So how many number of people this virus can infect in this course of disease, and when can this number peak? Because we are all worried about this number. It's not some hypothetical questions. We are all worried about these numbers in our daily life these days. When will this number peak? And after the peak, the ray of hope of the diminishing numbers will come. And we are taking a lot of mitigation strategies. And what are the impacts numerically these mitigation strategies can have in these numbers? So to answer these questions, there's a branch of science called epidemiology, which tries to answer these questions by mathematically formulating epidemic growth. And the starting point of this mathematical formulation is to understand certain time variables. So this black line is a time axis. This represents the time axis. And these colored dots represent certain points in time. The red dot is the time at which a person comes in contact with a source of infection and the virus starts breeding inside this body. And since the time of source of contact with the source of infection till the onset of symptom, which is this yellow dot, which I'm pointing to, is called the incubation period, which is represented by TE. So at this point of time, the person starts showing symptoms. So everybody was susceptible before this red dot. Once he or she becomes in contact with the source of infection, the virus gets into his body and starts bleeding. And on this time, the symptoms start showing. Since the time of onset of symptoms till the recovery is called the recovery time. This TS is the recovery time. Interestingly, the person is contagious not during the entire duration of this time, but starting from a point denoted by this orange dot till this light green dot. So possibly one day prior to the onset of symptom, he starts infecting to others, and it keeps on infecting for some duration of time. And this duration of time is called the period of infectiousness, TI, denoted by TI. And unlike certain other diseases, for SARS-CoV-2, even prior to the onset of symptom, the person starts infecting. Okay. So the typical numbers of these periods are given here. Let's make some simplification. Let's set this TP, which is the pre-symptomatic period, the overlap between the period of infectiousness and the period of incubation, TP, as 0. So that means we assume that only since the time of onset of symptom, the person starts transmitting the diseases. And second simplification that we make is, after the period of infectiousness is over, we remove that person out of the system. Why is it okay to do that? Because once the person ceases to transmit disease, as far as the study of growth of infection is concerned, he is no longer contributing the disease to anyone. So if you're interested in the study of growth of the epidemic, once the period of infectiousness is over, he can be considered as recovered, or he can be maybe a different word is of use here. He can be considered as removed out of the system. So that boils down to splitting the time axis into 4 compartments. The first is susceptible compartment, which everybody will be belonging to. And once he comes in contact with the virus and the virus starts bleeding, he will be called an exposed person. Since the onset of symptom, he starts transmitting the disease and he'll be called an infectious person. And once the period of infectious is over, he is removed out of the system. So these compartments, let's call S, E, I, and R compartments. And 2 assumptions that we have made here is that the population remains closed. That means nobody comes out of this system and goes somewhere else in the meantime, or no other person comes into the system. This is slightly not unrealistic, but suppose the borders are shut and all those things, we can assume that it's a closed population. And second assumption, which is more important, is that the source of the interaction between the source of infection and the susceptible person leads to disease transmission, right? And here we assume that the people are homogeneously mixed, which means that everybody interacts with everyone else in the same manner. Okay, so now let's start looking at the dynamics of.
Birenjith, this is Amit. Sorry to interrupt. Just
Yeah.
one question on the previous slide. So once I get recovered, you're not. So even though I continue to be part of the homogeneous population, or mixed population, I don't end up being the one who's going to be susceptible, right? Is that
No. Because it's a viral infection. Viral infection, once it comes, you become immune forever.
okay? Fine.
Unlike bacterial infection. Fine.
Okay.
Good question. So you have this compartmental model depicted with the help of this picture. Now let's understand the dynamics of each of the sizes of these compartments. So with a slight abuse of notation, let me call S, E, I, and R to represent the size of this population also. Okay, so S, T, E, T, I, T, and R, T, they represent the size of each of the compartment. And N, capital N, is the total size of the population. And clearly, N is sum of ST plus ET plus IT plus RT. And the normalized variables, that means the ratio of S to N, S divided by N, let's call with small s, little e, little I, and little rt respectively. These are all normalized population size variables. Now we are interested in finding the dynamics of these functions of time. Okay, to understand that, let's look at a single susceptible person and see how the disease spreading happens from the other source of infection. So this person in the middle is a susceptible person. And let's see denote the average number of contacts he makes per day. So C is an average number of contacts the susceptible person makes per day. Now, out of these contacts she makes, a fraction of the people can be potentially infectious. Okay. And what is the best estimate to find out this fraction? The best estimate could be the current proportion of the infected people in the whole population, which is I by N. So I by N is the current population of the fraction of infected people in the entire population, and that we will take it as the number of infectious contacts for everybody. This is where this homogeneous assumption plays a role. And out of the infectious contacts he makes, here it is 3, there is again a probability that the transmission happens, which is the alpha. Okay. Once this is understood, we are ready to write the equation for the dynamics of the S variable. So this, the description which I have made is for a single person. Now for everybody who are susceptible, this picture is applicable. So the total number of infection that happens per day is alpha into C into I by N into the entire susceptible population. So alpha into C into I by N into S is the total number of infection that can happen per day. And every infection is an outflow from the S compartment. So if you are a susceptible person, when you become infected or when you become exposed to the source of infection, you get into the E compartment. So it's an outflow. So the rate of change of S is nothing but a negative of alpha into C into I by N into S. And let's define alpha C as beta, which is minus beta into I by N into S. Just representing in terms of normalized variable, this will become ds by dt equal to minus beta is. So this beta I by N is the rate of outflow from S to E. Now let's understand the further outflow to I and R compartments.
Birenjith, there's one question, Amit
Yeah.
here, but from a different person. So the question is, how is I calculated? And secondly, is it fixed or dependent on the population density?
I is a function of time. Here, even though I didn't mention this IT, I is a function of time. The calculation of I is a whole game that we are after. Okay, how I grows and I comes down. I is the infectious, the number of infected people. Is that answering your question or? So, Amit,
Yeah, I think you can proceed. This was a chat question, so it might be
okay.
for the.
Okay, but this should be very clear. I is the number of infected people at a time t. Okay, so suppose a person is a susceptible person. Once he becomes infected, what is the source of infection? The source of infection is the number of infected people at that particular point of time. Through the interaction with the people in I compartment, a person in the susceptible compartment moves to the E compartment. So I is the number of infected people at a particular point of time. IT is the size of infectious population. Okay, so let's move on. So now we are interested in the progression from E to I compartments and subsequently from I to R compartment. But these progressions are quite deterministic. If you become an exposed person, invariably after the incubation period, you will become infectious. There's nothing stopping that. There's a chance of there's a chance involved in the migration from S to E, whereas there's no chance involved for the migration from E to I or I to R. Okay. So after the infectious period of incubation, a person will move from E to I. So let T be the number of days of incubation period. Then at a rate of 1 over T, people move from E to I per day. So 1 over T is a progression rate, or it's the fraction of exposed turning infectious per day. Similarly, from I to R movement is also quite deterministic. So after the removal day, number of days, which is Ti, person will move from I to R. So here we assume that there's no death or anything. Even if it is death, it can be incorporated in the model as though it's a removal. Death can be characterized as a removal actually. So R is not just recovery, it's getting removed out of the system. So 1 over Ti, where Ti is the period of infectiousness, is the rate at which people migrate from I compartment to R compartment. So this is quite straightforward, and we can write the the derivatives for E, I, and R. So let's write the second equation of capturing the dynamics of the system, which is the rate of change of E compartment. So dE by dt is, so the change in E is because of the inflow from S as well as outflow into I. So inflow from S is already described, which is beta is by n, and outflow into I is minus rho E, because where rho is the progression rate or 1 over incubation period. So this is nothing but the differential equation corresponding to the dynamics of E compartment. If these two are understood, the remaining is quite straightforward. The rate of change of I is inflow into I minus outflow out of I. And the inflow into I is nothing but the outflow of E, which is rho E minus gamma I. And the dynamics of R is just inflow only, which is gamma I. So these four equations, one which we mentioned in the last slide, SEIR 1, and the 3 mentioned here forms a system of nonlinear differential equations, and that captures the dynamics of this deterministic compartmental SEIR model. Now the point is to
Shashank here. Yeah. So one question in this. So you also have an arrow from I to S with labeled by a C.
Yeah. This means that the outflow from S to E is because of the interaction from I and S. So it's confusing. It does not capture any actual physical movement of people. It just captures the interaction.
Sure. It's the infected people who make the susceptible people
Exactly.
Okay, great. Thanks.
And one question, you're calling this system non-linear because of this term I into S? Because
Exactly.
rest all the terms I'm seeing them as linear.
Precisely.
Okay.
Precisely. Okay. So now,
Birenjith, Amit, okay.
yeah,
Sorry to
please.
interrupt again. So
Yeah, that's fine.
call it the deterministic part. So perhaps you will explain, but what is the deterministic thing here exactly? Which one are you alluding to?
Yeah, because even though, see this alpha, I said it's a chance of transmission is. I'm taking this alpha as a chance of transmission, which is kept as a fixed constant in this model. Okay, but later in a later model, which we will see towards the end of this talk, we will introduce something called stochastic agent-based model, where we will see a probabilistic modeling of epidemic.
Okay.
I think then it will be very clear. Okay.
So Biren, please correct me if I'm wrong. So I guess, I mean, this is kind of capturing the average statistics of
Yes.
everything, right? So
Yeah, it captures the average. Okay, so we are interested in solving this system of nonlinear differential equation. So let us represent the SEIR as a single vector variable and write down the system of nonlinear differential equation as a matrix vector product manner. And then this is the matrix that you will obtain, which of course is having an ST term, as pointed out by Lalitha, is the nonlinearity. So this is it depends on S as well as it's a time varying function. This matrix is a time varying matrix. That is the biggest problem that we have. So the initial phase of this growth, however, can be characterized by approximating this equation into a linear one. So suppose the initial condition ST is, or S at t equal to 0, let's say S0 remains constant for some duration of time, maybe. So typically it's nothing but S by n. S0 is S by n at t equal to 0. So usually the entire population is susceptible initially, except for a few infectious people who landed into the community from somewhere else. So maybe this will be some 99.999% are susceptible, and that is this S0. Once that assumption is made, this matrix will become a constant matrix. Once it becomes a constant matrix, you can do eigenvalue decomposition of this matrix f S0 at time equal to 0 and write as P lambda P inverse. After that, you can do a variable transformation onto this vector as S1 E1 I1 R1 as P inverse SEIR to diagonalize the entire system. Now, the derivatives on the left of S1 E1 I1 R1 variable is related to the current state S1 E1 I1 R1 via multiplication by a diagonal matrix. So essentially the system splits. So this can be done at the initial phase. So let's try to do this for this particular SEIR model. We're doing the eigenvalue decomposition, which is quite simple to do. It's clearly because it has two Alzheimer columns, two eigenvalues turn out to be 0. So the essential matrix that remains is this, which I call F1, is just what is the 2x2 block taken from inside of this Fs0. And you can compute the eigenvalues, and that will be nothing but this numbers, which is, so you don't need to worry about these numbers too much, but I'll direct you to the factors that you have to be worried about. So anyway, the point is that the eigenvalues can be easily computed. So once the eigenvalues are computed, it's a because of the diagonalization, you can solve the variables S1, E1, I1 and R1. Let me go back. S1, E1, I1 and R1 quite easily, because the equation is something like S1 derivative of S1 is equal to some constant into S1, which will give you exponential solution, exponential as a solution. So S1 can be found out, E1 can be found out, I1 can be, and R1 can also be found out. Then you have to convert back to S, E, I, and R. So essentially, you will get the linear combination of the exponential that are resultant out of solving this. And because it's of that form, the largest eigenvalue will contribute because that will be the leading exponential term. If you follow this much, then it is easy to write that the growth of IT is I0 into e raised to lambda 1 t, where lambda 1 is the largest eigenvalue of that particular matrix we described. And which is this. Now, we are interested in knowing when this curve will grow at the initial phase. The growth will happen if this particular part of this expression, which is rho into beta S0 minus gamma, is greater than 0. So the epidemic curve will grow if this particular factor is greater than 0 or beta S0 by gamma greater than 1. So you can forget all these eigenvalue expressions. Just keep your focus on this parameter, beta S0 by gamma. If it is greater than 1, then you will have a growth in the initial phase. Yeah.
Birenjith, so what was beta and gamma here? So S0 was the initial population. What was beta?
Good. Maybe we can revise that once. Beta was this constant, which is the constant which appears in the the constant that appears in the dynamics of S. Okay. Beta is the constant that appears in the first equation of the SEIR model.
Okay.
And gamma is the recovery rate. Recovery rate is 1 by period of infectiousness. And rho is the progression rate, which is 1 by incubation period. So let's recall those things because Amit has anyway asked. Rho is 1 by incubation period. Gamma is 1 by period of infectiousness. Beta is the factor that comes in the first equation that captures the dynamics of susceptible to S to E migration. Okay. So fine. So okay, so we were here. So
we also say this in words. How would I mean, I just want to understand this. So it's like beta S0 should be greater than gamma. Is that the right way to interpret
it? No, in fact, that's where we are heading to, understanding this term. Okay, so let's understand that term because anyway, Amit has asked, and anyway, that's the natural direction we have to head to. Okay, so let's, so beta S0 by gamma turns out to be an important number, and that number we call the basic reproduction number. Okay, so let's try to understand this number quite a little closer. So assume that S0 is 1 to start with, because initially it's an initial phase and most of the people are susceptible. So S0 is 1. So we take S0 as 1 and then this expression will become beta by gamma, and that is your R0. I'm sorry if I mentioned it as beta S0 by gamma. It's beta by gamma is R0, which is a basic reproduction number. And beta, as we already mentioned, it is alpha into C. It was alpha into C. Let's try to recall that again. Beta was alpha into C, where C is the average number of contacts you make, and alpha is the chance of infection if you make the contact. And gamma was 1 by Ti. So 1 by gamma is Ti. So essentially beta by gamma is nothing but alpha into C into Ti, which is alpha is the infectivity into number of contacts you make per day into period of infectiousness. So infectivity into number of contacts you make per day into period of infectiousness, which is infectivity into contacts over period of infectiousness. So that means, suppose a susceptible person, or suppose an infected person, so just think from the point of view of an infected person, he makes C contacts per day and he is infectious for a period of infectiousness. So contacts over the period of infectiousness is the disease causing contacts he makes. Okay. Because he'll be infectious over the period of infectiousness. So number of contacts over period of is the disease causing contacts he makes. And there's a chance of infection. Not all disease making contacts turn to infections, transmission. The chance of infection is infectivity, which is alpha. So this is actually the number of infections generated by an infectious person. So this number is R0 is nothing but the average number of infections generated by an infectious person. So ultimately, what it says is that if the average number of infections generated by an infectious person is greater than 1, then the epidemic will grow. Okay, and this is a very realistic number to estimate from the ground. R0 you can actually estimate with the help of surveying on the ground. And that is a very interesting and important problem to do. And in fact, we have done that. We have chosen a district in Kerala, and we have made surveys with roughly 200 people, and tried to estimate this number also. And we got something around 2.1. So roughly, every person infects 2.1 persons on an average. And estimating this R0 during epidemic and the post-epidemic period is it's an important problem of interest in epidemiology, and people spend a lot of effort in doing that. In fact, we did this with the help of survey and also by using some machine learning algorithms as well. From the data, we tried to learn this R0, and fortunately, they matched. With the help of survey, the estimation we did, and in fact, the learning part we didn't do. Another team from IIT Palakkad, led by Brunal and Sahili, did, who are also working along with us, did the learning from the real data. Okay. So that's the initial part. But
one question here. So any reason this is called R0? Like the zero, does it emphasize anything? I know S0 was the initial population you assumed.
Yes. Normalized. So one of the reasons is that, in fact, it's the R0 that will change, that will keep changing. Okay. So see.
R0 is a function of time.
It's the initial. See, it was it was beta S0 by gamma that was the most important thing, right? So if you at a middle time, you can talk about beta ST by gamma. What is the proportion? What is the susceptible fraction ST? So beta ST by gamma would be the deciding factor if you sample the epidemic growth at an intermediate time. So, so that way, that is called RT actually. That is not R0. That is called RT. Beta ST by gamma is called RT. So your reproduction number at that point of time. So that's why it's called R0.
Okay.
So okay.
There was one other question here. Sorry to interrupt again. There was one other question. The question is, how is the infectivity calculated, or is it estimated?
Again, people do learning algorithms to calculate the infectivity. We also did that. It comes to some 3% or something. These are actually the difficult problem in these epidemic growth studies are finding these numbers actually, not the mathematics which I am describing. The difficult part or the challenging part is finding these numbers which are actually realistic with respect to the actual dynamics of the disease on the ground. So there are various methods, but that forms another topic of study itself. Okay, so initial growth is what we discussed so far, but of course this initial phase is not the way the system behaves in the long run, because we made a strong assumption that the matrix remains constant. It is not. The matrix keeps varying as the ST changes. So it's a nonlinear dynamics. So there is no solution so far available for the system of equations. There are approximate solutions, some of which we will also see in this talk. But the only way to simulate it, and if you simulate this nonlinear system of dynamics, you can get these curves actually. This is simulated for certain particular values of beta, rho, and gamma, assuming R0 is 1. So if you have beta, gamma, and rho and gamma and beta, then R0 can be determined actually. It's beta by gamma. And S0 is taken as 99.99%. And here SEIR are plotted, and see the I, which is the red curve, it grows, and then after some point of time it starts decreasing. And I would like to invite your attention to I and R. I is the number of infectious people at a particular point of time. On 150th day, I is this value. That means on 150th day, these many number of people are infectious in the society. Whereas R is the number of recovered people. That means this green curve captures the number of people who have become infected and after that got recovered. So what is the number of people in the society who actually got infected, who got the disease? To know that, you should look at the R curve. So for example, in this example, see, this is 70, this is 70, right? Roughly 70. Yeah. 70% of the people got infected some point or other, because that means that's why they have come to the recovered compartment. Okay, so as I mentioned, this is done using simulation, but some of the numbers can be theoretically computed. So 2 examples I would like to highlight. If becomes complicated, we can skip also, but let's see. Let me make an attempt. So these are heuristics actually. So let's try to find out this peak value, for example. So I'll try to find out this peak value, and this is called R infinity, the final value of R analytically, with the help of some heuristics.
Biren, one question, if that is okay. In the previous curve, I mean, if you do the cumulative addition of the red curve, do you get the green curve, or is it different?
It's different.
So
it's different. It's different because the I is slightly tricky, because suppose today I am infected, so I am counted today also. Tomorrow also I am infected, so I will show that also.
Okay.
So you will be overcounting if you integrate or.
Okay.
So now, okay, let's try to compute the peak value and the R infinity with the help of some heuristics. So suppose, so if you, hopefully you remember the equation, let me just go back and show the equations again. So this is the ds by dt equal to minus beta is, and dr by dt is gamma I. So now what I'll do is I'll divide these 2 equations, SEIR1 and SEIR4. Then I will get cancelled. That's why. So beta is here, there's a beta is in the RHS, and here gamma in the RHS. That is what I'm doing. And then you will get an expression like ds by dr, assuming all the functions are analytic and all those things. Ds by dr is gamma r, a constant into r. So that will give you help you solve S as a function of R. So S can be solved as a function of R in this manner. Once you do that, you can write E plus I is equal to 1 minus R minus S, because R plus S plus E plus I is 1. So E plus I is 1 minus R minus S, which is 1 minus R minus S0 e raised to minus R0 R. Now at the peak, this particular number E plus I is maximum. So that is where one of the heuristic is applied. The heuristic is that you assume that both E and I hit the maximum simultaneously, which is what you saw in the picture. See, the E and I almost simultaneously hit the peak. So E plus I also hit the peak at the same time. And once you do that, you can take the derivative here and you can solve it. You will get the maximum value of E plus I. Once you get the maximum value of E plus I, you can get I max again by setting di by dt equal to 0, which will give you, so if you set di by dt equal to 0, you will get rho E by minus gamma equal to 0, because di by dt 0 means the inflow and outflow of I compartment remain the same. Which means rho E minus gamma is equal to 0, and that helps you proportionate I as a fraction of E plus I, and then you can get a rough idea of I max. So you get E plus I max with the help of dividing SEIR1 and SEIR3 and do some tricks, and finally you get proportionate value of I max, setting di by dt equals. So this is not, if you didn't properly follow it, it's fine. I'll anyway share the slides. This is not very complicated. So that is one thing. To validate this, that where E and I simultaneously hit the peak, you can try plotting it for various beta gamma values. You can fairly see that most of the time E and I hit maximum almost simultaneously. The second and most important, another important parameter is the final epidemic size. As I said, the R infinity. So this is very important because at presently, what people are interested is, suppose you have a town, and suppose as far as the epidemic growth of that town is concerned, it has hit the R infinity. That means the curve has started flattening or something. In the sense, the R curve, not the I curve. The R curve. The I curve may be fluctuating, but R curve is flattening. That means 70% of the people are already infected. Then you can open that down and make them free instead of locking them down. So it's important to know when a particular population has become saturated. And towards that, estimating this R infinity of health. Maybe some panchayats have already saturated. Then why don't just let them go around? In fact, that is good also, because when they go around, it will help you boost the herd immunity actually, because they have already passed through the phase, and now if you allow them to merge the other population, the herd immunity of the other population will get enhanced. Anyway, so these parameters are important, which is R infinity, which is limit t tends to infinity RT. So one way to find out this parameter is, it's very interesting actually. It's brilliant. This particular paper, they have found out this R-infinity. Somehow I like it very much. So the way they have done is that they somehow find out, cleverly, they find out a parameter which is time invariant. So just looking at those equations, 4 equations, if you look at gamma by beta log S plus E plus I, you will get that it's a function independent of time. It's a constant. It just comes from those 4 equations. You can just see that. You can just see that, compute these quantities, and it will be independent of time. So then you can write down this value at 2 different times, and it has to remain constant. So I'll write down the values at S0 and S infinity. This is gamma by beta log S infinity plus S infinity. And E and I at t equal to infinity, ultimately they'll die down. There'll be no infected and exposed people at that time. So they are 0, which is gamma by beta log S0 plus S0 plus E0 plus I0, and just do some arithmetic manipulations, and you will see that ln S infinity equal to R0 S infinity minus 1 plus ln S0. And then you plot this taking S infinity as a variable, you plot these 2 curves. This is a linear in S infinity, and this is a logarithmic S infinity. You plot those 2 curves. Wherever they meet, that is your S infinity. Once you get the S infinity, R infinity is 1 minus S infinity, because E infinity and I infinities are 0. So this is the way you can easily, this is exact, this is not heuristic, this is exact. And this way you can compute the fraction of the entire population that will finally get infected. So that it's a total fraction of the people who will finally end up infected, maybe 70%, 80%. Okay, so this winds up the first section of my talk, which is the basics deterministic SEIR model. So, an important assumption that we made in the whole setting was that the population is homogeneous. Everybody interacts with everyone else in the same manner, which is obviously true, obviously false, you all agree. So, how can we try to emulate the real population into this model? One way is to split this population into subpopulation, which are inherently homogeneous, but they don't interact to each other in a homogeneous manner. So, for example, districts in a state. So these are mnemonics for district in Kerala, where we conducted the study. So these districts we assume as homogeneous populations, and they interact with each other in a different amount of strengths. See, for example, close by district, the strength of contact will be large, whereas districts which are not close by, the strength of contact is less. So this way, a toy model to start studying this metapopulation. This is called metapopulation model. A toy model to start studying is with the help of two subpopulation. So you have two SEIR deterministic models: S1 E1 I1 R1, S2 E2 I2 R2, and within them they behave simply as an SEIR model. However, there are cross interactions. For example, I1 interacts with S1 naturally, but there is an interaction from I1 to S2. The infected people in the first subpopulation can possibly interact with the susceptible people in the second subpopulation, and vice versa. So this, of course, enhances the number of equations as the number of subpopulation that you are considering. Here you have two subpopulation with N1 and N2 are the population sizes. Then the equation almost remain the same as far as the I and R dynamics are concerned, because I and R dynamics only does not have a role of the contacts that are made, whereas the equation changes as far as the dynamics of S and E are concerned. So the rate of reduction of susceptible population in the first compartment is not just contributed due to the interaction with the first population, but also contributed due to the interaction with the second population. That's why you have a constant Cj1, which is the contact rate with the first subpopulation, into I1 by N1, and Cj2, which is the contact rate with respect to the second population, into I2 by N2. So these terms will appear here. And exactly the same terms will appear while capturing the dynamics of E compartment, because outflow of S is inflow of E. So this is quite simple to understand, even though the equations are slightly cumbersome. The idea is very simple. Now again, you can try to attack this problem in the initial phase and the longer run separately. You can look at the matrix, and it will be an 8 by 8 matrix, and some columns will be all 0. Removing that those columns, you will end up in a 4 by 4 matrix, which is essential part of that matrix. And you are interested in computing the determinant of this F1 minus lambda 8, because you want to compute the eigenvalues of this matrix. And that also comes out in a nice manner. So this is some calculations which I'll skip through slightly faster manner, because anyway I'll share the slides. You can go through these if you're interested. So if you do some normal matrix arithmetic, it will so turn out that you have to find the determinant of a submatrix. Actually, submatrix. This is the matrix. This is quite straightforward. I don't think there's any principle involved in this slide, so I'll just skim through this and get to the final answer. And what it ultimately comes down to is that it will come down to an equation of this form: lambda plus rho into lambda plus gamma plus rho by rho is equal to lambda c, where this lambda c is the eigenvalue of a matrix formed like this: beta 11 S1 by N1 into beta 12 S1 by N2, beta 21 S2 by N1, and beta 22 S2 by N1. And these betas are nothing but alpha into C11. So, because you have contacts C11, C12, C21, and C22. Beta 1 is alpha into C11. And this is S1 by N1, S1 by N2, S2 by N1, and S2 by N2. And this can be written in slightly different manner, as given here. And this lambda c is the eigenvalue of this matrix M. And because eigenvalues remain the same, even if you shift the multiplication cyclically, you can see that this lambda c is same as the eigenvalue of matrix obtained by multiplying this and this together first and then multiplying by this. So you get S1 by N1, 0, 0, S2 by N2, beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2. And this S1 by N1 is the initial fraction of susceptible, which I call S10. And S2 by N2 is the initial fraction of susceptible, which I call S20. And the beta values. Beta is alpha C1, alpha C11, alpha C12, alpha C2, and alpha C22. Why I spend this much time on explaining this is because exactly the same equation we had earlier. Go back. Eigenvalue of F1, the essential matrix F1, was computed in the single community case, and then we had the determined calculation will lead to lambda plus rho into lambda plus gamma by rho is equal to beta S naught. This was the equation we had, and that led to the computation of the eigenvalues. In the two community case also, you get a quite similar kind of an equation. Come back here. Here, the same equation where the RHS is it was beta S naught earlier. It's replaced by lambda c, where lambda c is nothing but the eigenvalue of this particular matrix. So it was, if it was an 1/1 matrix, it would have been S0 into beta. A single 1/1 matrix, S0 into beta, and that would be the eigenvalue of, because it's a 1/1 matrix, eigenvalue is also the same value, which would have come here. So the scaling from one community to two community, as far as the initial growth is concerned, it happens naturally. That is the point that you should take. That's the only takeaway from all this discussion. Okay, so once you realize that, you can generalize to multiple community model as far as the initial growth is concerned, because this can be easily generalized for multiple communities. This is only for the initial phase growth. So the initial phase growth, for the initial phase growth, the eigenvalues of the essential matrix can be computed. It follows exactly the same formula as we derived for the single community case, except that beta S naught is replaced by eigenvalues of a different matrix. And with the help of these, once you realize these eigenvalues, you can again define the R naught values for two community cases also. And here you will have multiple R naught values because there will be two eigenvalues for this M1 matrix. Okay. And the epidemic growth will be decided by these multiple R naught values. And in fact, it will be a linear combination of multiple exponentials decided by many R naught values. Okay. And it will so happen that outbreaks in one community can transmitted to an outbreak in another community. So all these things, the initial growth can be verified with the help of some examples. You can, which I have plotted here for various values of initial, the C values, various values of the contact matrix values. So this contact matrix is means that the C is diagonal, means that there's no cross community contacts, and this is no cross community contact, and you have initial infection at only one subpopulation. Then of course only one population will grow, the other population will remain the same. Here also there is no cross community contact, whereas initial infection happens at both the communities, then both will grow. Here there is cross community contact, and initial infection is only in one subpopulation, but you can clearly see that the outbreak in one subpopulation will transmit it to the second subpopulation, and the growth will happen. So these behaviors can be studied in detail with the help of examples and with the help of actual values of subpopulations. Okay, but other than the initial growth study, it becomes extremely complex to solve the entire system of equations, and only simulations are where we can find some. Is only with the help of simulation we can find some solutions. So one question that is of interest at this point of time.
Birenjith, Amritalok here. Sorry to interrupt.
Yeah.
So can we again determine the R infinities for both of these communities?
Not tricky. It's not easy. It's not easy actually. It's not. There's no. There are some heuristic approximation people make, but unlike the single SEIR case, this is not solvable. Of course, you can simulate, but it's not analytically solvable. Okay, so now, yeah, sure.
I know they are very dependent on what parameters are chosen, but in general, if you had a single isolated community and instead you had a coupling of two communities, do the R infinity values kind of look different for these kind of typical comparable communities? I don't know what the right comparison is, but like, for example, if they're closely interacting, does it make sense to wait for a lower R infinity value before, let's say, like you said, open up the lockdown? Because then you're okay, or do you still use typically the same values as in the isolated case?
See, this R infinity generally it depends only on the R naught. It depends on the R naught only, because all this, it says beta, gamma, all these things are remains the same for the population actually. This incubation period does not change actually. It's a virus specific property. The recovery rate also it's somewhat virus specific and the community specific actually, because the communities in general if it is they're more immune, they're resistive and all, then it has a little bit role. But what matters is that see, the infectivity parameter, the alpha, which is chance of infection, right? And the C, which is an average number of contacts you make per day, that can be adjusted actually. The alpha and C is under your control. So when you're washing your hands or when you're wearing a mask, actually you are reducing the alpha. And when you are not meeting the people, you are actually reducing the C. So C and alpha are under your control. And that is what all the mitigation strategies are can be classified as either adjusting alpha or adjusting C. And that way, this R naught or RT in general, RT is the reproduction number, dynamic reproduction number. RT can be adjusted actually. So this adjustment in RT in the meantime can completely change the fluctuation of this dynamic, this system, which is actually will make things again complicated actually. But still that's the way things will work.
I mean, so are there any, can this be generalized easily to, let's say, when alpha and C are also functions of time?
In fact, the stochastic agent-based model is towards that actually. The alpha and C actually is stochastically determined actually. But other than that, I don't know how, I don't have a good answer for your question actually. Maybe it's possible, but I'm not very sure.
Okay.
Okay, so two important aspects regarding this multiple community SEIR model is how to model the contact matrix. So we had pointed out C11, C12, C21, and C22, etc. How to model these values. See, if it had been a single community, you can talk about, you can somehow, that's also difficult, but you can maybe you can say actually there are standard studies actually. For example, in India, the average number of contacts a person makes per day is, from an epidemiological point of view, is found out to be 13. You make not in the lockdown condition, the normal time. You make interaction with 13 people closely. That's the usual average in India. But that is under assumption of a homogeneous assumption. It's an average number, so it's kind of homogeneous assumption is there. But now you're asking about cross-population interaction, which mostly depend on people traveling for job from one town to another and things like that. So this cross contact, how to model this cross contact is an important aspect if you have to set up a multi-community SEIR model. And what I am going to talk next is some aspects regarding that. There is something called transport model, which tries to model these kind of cross-town interactions. So let there be M regions, R1, and let's call that at R1, R2 up to Rm, with respect to subpopulations N1, N2 up to Nm. We say a person travels from Ri to Rj if she lives in Ri and goes daily for a work in Rj, because you are always worried about the average contact per day. So that's why these kind of definitions comes. Now let Ti be the number of people traveling out of Ri, okay, and Ji be the number of job opportunities in Ri, okay, and Dij is the distance between Ri and Rj. And whereas Ti was the number of people traveling out of Ri, Tij is the number of people traveling out of Ri but going to Rj. So you can his region can also be, you can think it as districts. So from Hyderabad, people travel to some other nearby district, things like that. So these numbers, suppose you have these numbers, the total number of people traveling out of every district, the total number of job opportunities in every district, and the pairwise distance between districts. Suppose we have these three numbers, Ti, Ji, and Dij. And the importance of assuming the knowledge of these parameters, that these data are actually captured in census. The number of people traveling for work from every district to other district is actually captured in, and there is splitting up of like for which job they travel, non-agricultural job, like teaching job, that is also captured in the census actually. And of course, the mutual pairwise distance are available, and the number of job opportunities in every town, that is also captured in census. So suppose these numbers are available, then the gravity model for transport tries to find out an estimate of region to region travel in this manner. So the people traveling from I to J is proportional to the total number of people traveling out into the number of jobs in the place where they are traveling to, divided by Dij square, divided by the distance square. That's why it's called the gravity. The distance square comes beneath. So this is a very standard model which is used to estimate the fraction of people who travel from a particular region to another region actually. And the whole point is so usually what they do is they multiply by a constant also, this Ti into mu, which I have not put here, and they appropriate this constant to match the actual data also. So this is a very quite standard model, but it may appear very childish, but it so turned out that we had a very slightly complicated model later, and we ventured with that complicated model. It so turned out that the simple model worked better actually, so we reverted back. So the complicated model is something called radiation model. The radiation model actually tries to do something more cleverer. So here again, Ti is the number of people traveling out of Ri. Ji again is the number of job opportunities in Ri. Dij is the distance between Ri and Rj. That's fine. They're all same. Tij is what we are trying to estimate, the number of people traveling from Ri to a particular Rj. That will be estimated with the help of a little bit complicated formula. And this complicated formula comes as an outcome of the model which I am going to describe. What everybody does is actually, everybody samples a job from a salary distribution FZ. Okay, while deciding his job, he samples from a salary distribution. So suppose a fraction of people decides to move out of his town and find a job in a remote town, maybe a city or something like that. Then what she does is she keeps sampling the salaries of sampling jobs in nearby towns. Maybe she'll first sample jobs from the nearest town, and she'll keep doing that until she finds a job that pays more than the highest paying job in her own region. RI. So if she decides to travel out of her hometown RI, she chooses a job that pays more than the highest paying job in her own region RI. Okay. So two things are important. I think I missed out one thing. Okay. So she chooses a job in the nearest town that pays more than the highest paying job in her own RI. So essentially, what she does is that suppose what she knows what is the maximum salary she can obtain in her own town. Okay. She has decided to move out of the town, and she keeps sampling the next town job in the next town, and she gets a higher paying job in the next town. Okay. And then she again goes to the further next town and keeps sampling like that. Now she'll pick a job which is highest paying job than whatever offered by the maximum paying job in her own town, and which is nearest. So both conditions she'll try to satisfy. And this is what the radiation model does. And it can be shown that if the salary distribution is constant for every town, it can be shown that the Tij can be estimated in this manner. Ji into Jj by Ji plus Sij into Ji plus Jj plus Sij. Where Sij is a number of jobs in all region except Ri that are closer to Ri than Rj. So if this is too distracting, just leave it. Anyway, we tried this model hard, but it did not give us good result. And finally, we realized that the whole flaw of this model is that the job salary distribution is kept same for all the towns, whereas it's not commonsensical, because the cities will have a different job distribution and the town panchayats will have a different job distribution. And then we try to work with different job distribution. Then the proof turned out to be very tricky, and we left that. Anyway, so this is a recent model for estimating the Tij values. Now, if you have these Tij values estimated, the whole game is to map these Tij values into the contact values, which can be done by proportionation and in using simple math, and that will get you the cross contact values. So this is the usual way people do the cross contact estimation. Okay, so finally, this is what the point I would like to end the metapopulation model description. And in fact, this ends up with more questions than answers. There is no open clear-cut solution for finding the peak of subpopulation. You can only simulate. So is there any way you can approximate the relative delay between two subpopulations peaking? That is one aspect we looked at, but we could not find out an analytical characterization of that. At the same time, we try to make to study this asymptotically. Like suppose the number of subpopulation increases to infinity, what can you answer some questions? Even that failed, to be honest. So it left out with more questions than answers. When these are all open questions in this field of epidemiology. Okay, so that winds up my what I want to describe about the deterministic models, and let's move on to some other different category of model called stochastic age-based model. What is the time now?
Biren? Yeah, so it's actually 4:45 now.
Okay, 4:45.
Yeah.
Okay, then what I will do is that I will skip this and just maybe I'll wind up in 5 minutes actually.
Sure.
No, not even 5 minutes.
Take-
Maybe
take
3
time.
minutes.
Sure.
I'll wind. Okay. So what I'll do, only thing I want to mention about in the stochastic age-based model is what it is and an open problem in that. So that's all I will do, because which is a very interesting problem, at least in my perspective. So the way it is done is that you instantiate individuals. So here, stochastic age-based model, you instantiate individuals. An individual will have some attributes: age, sex, employment status, etc. So you instantiate this individual drawing from certain probability, joint probability distribution of these attributes. And once these individuals are, maybe 1 lakh individual you instantiate. Okay. Once you instantiate these individuals, you associate with these individuals certain social institutions. Okay. So, for example, every individual will be associated to H households, maybe 100 households. Also, she may be associated with W wards, your municipal wards. So you make these associations. Okay. Once this association is made, okay, here is where one of the very interesting problem actually. See, you have instantiated this individual with respect to some probability distribution, right? Now, you assign edges in this bipartite graph to make the associations. The interesting thing that can happen is that, see, you have made, so this particular, see, person 1 will be associated to maybe H1, house 1. Person 2 to maybe H3, like that association is made. But you have a marginal distribution on age because you sampled from a joint distribution. But the association demands a conditional distribution on the age. What does that mean? Given a household, usually half of the guys are male and half of the guys are female, or something like that. You cannot have all the females in a particular household. Similar in a particular ward. So there are certain conditional distribution that has to be enforced while doing this edge assignment, which becomes tricky when you have to make multiple, you have to satisfy multiple bipartite graph association. So this is a very interesting problem in stochastic Bayesian-based modeling actually. So that's the only problem I can figure it out. Okay, later part, the infection spread, the way it happens is that it happens probabilistically. In every time you discretize the time to delta t, and then in every time period delta t, there's a probability for a person to transition from S state to E state, and that probability, because you model the wait time as an exponential random variable, that probability is nothing but 1 minus lambda into delta t, and this lambda rate and depends on a lot of things, your age, household size, etc., etc., and the disease progression afterward also, not the disease transmission, even the disease progression is also probabilistic. From E to I compartment, you move after a random delay T, and these random delays are modeled typically with either gamma, variable, or log normal distributions. Then mobility can be captured by changing the association graphs, the bipartite graphs time, and then finally you do the simulation. In fact, this is a simulation curve obtained by IAC team, Rajesh and Nitin team for Mumbai city. Okay, that winds up what I want to tell about stochastic game. And these are some of the simulators. The Prakriti simulator from IIT Delhi. This is also, I think, due to one IAC alumni, Anup Krishnan. And then this is NDSI simulator. IP address are given, you can try out on your own. And CTC simulator is due to IAC, they have studied Bombay City and Bangalore using stochastic model. COVID sim is the simulator due to us. We have actually have subpopulations in the panchayat wise, and we, the help of gravity model, we estimated the contacts, and we have a geotemporal simulation of the Kerala state. And there's a Govt of Kerala initiative due to KSW, wherein I worked, and we had another simulator actually, which is private. It's not publicly available, but whatever I mentioned so far is publicly available. Heuristics is another stochastic agent matrix model from IIT from Mumbai, actually, from a private university. Okay, with that I'll wind up. I'm sorry that I took a lot of time.
Thanks, Biren. That was a very nice talk. So if people have questions, then they can please unmute themselves and ask, or otherwise type it in the chat box. Yeah, so maybe while other people ask questions, in your you mentioned this interesting problem of that you have in modeling the stochastic agent-based simulator, right? And how do you choose the various conditional distributions?
Yeah. So yeah. Okay. Yeah. Please ask.
So why can't you do it like these people do in these document model kind of things, where you can have a distribution over wards? I mean, you can have a distribution of houses over wards, and a conditional distribution of populations within households. That's not a... So yeah, basically you draw maybe K wards, so W wards at random, and then in each ward you associate a certain random number of households, and in each household you draw a random number of individuals distributed according to a certain age, and could also depend on the ward. So condition of the household and the ward, you could draw individuals at random.
Yeah, the point is that how to do it efficiently. Yeah, I didn't. So you have 1 lakh. Because in SAM, you have a large number of agents actually. So how to do this edge assignment in an efficient manner that does not take much time. Most of the time it blows up, and people do some at least what Rajesh and team did. I talked to them in person, and they finally left this, and they do random assignment of edges, and then they goes and checks each households. If it is too much aberration from the actual household conditional distribution, they make some local adjustments. That's the way they do.
Okay.
Birenjith, I had a question. Abhitalo. So this is just going back to your original model, the deterministic case. So if I look at it, it's one way of looking at that model is I have, say, X is like the state of the system, then I can think of it like as a state estimation problem, right? Where
yes.
So one question is, I'm thinking from let's say a policy planner. Okay, what I want to know is there is going to be a peak like the R infinity value. But what I would like is, I don't care if the entire population gets it or whichever large fraction gets it. I want it to actually be in a manner where my medical facilities are not kind of overburdened. So I would like it to get to a path, kind of massage that curve to get to R infinity, assuming R infinity remains the same. So looking at it as the state estimation problem, is there some kind of an input, in the sense, something that I can control? Like you're right that I need to control the alphas and the beta, the alphas and the C's, sorry. So in general, a state equation, the way we write it is we say X is the state, so X dot. So derivative of X is A times the state X plus B times the state, the input U. Where U is something that allows you to drive the trajectory in a manner which is what you would like to do. So if I want to say my criteria is not to, let's say, overburden the hospitals, the same at a particular. So can I do anything on that by?
Yes, very good. Actually, this is the line of thought taken by you would have, maybe some of you would have, maybe you would have seen a group from IMSC Chennai, Adhikari and all, they had a paper, and what they took is this kind of control approach actually. They set up some control variables, and they tuned. I didn't quite understand that paper even though, that, but you can. I'll cite you that paper, and you can take a look at that paper. They have this quite similar approach.
Okay, but right now you're saying the alphas and the betas are in a way. So the policy planner will try to do something like a lockdown or some other local issues to control those alpha beta parameters.
Yeah, exactly.
Additional input that I have into a system. I just play around with the parameter.
Yes, they play around this parameter. This is the two parameter they play around, and and try to Most of the time, what happens is that if you play around with many alpha and C, the curve will go up, come down, and again it will go up because
yes.
It's as though you have a different S0 and you are starting afresh. Yeah.
So in a sense, the differential equation is kind of time invariant, right? So you can always simulate up to a certain point, and then change the parameters, and then continue the simulation, and the model still.
Yes,
valid,
yes,
right?
yes. That's correct. Only the S0 changes, and that is
correct. So it's as though you started fresh with a new system, but with the S of t that you have.
Exactly. So if your R0 RT is unless your RT have come down, come less than 1, it will again behave
exactly
to another peak.
Okay, so there's another question in the chat. So, like for asymptotic COVID cases, where like some of the population may act only as active, I guess. So there are some people who are asymptomatic, right?
Yes. So this is This is what all these kind of things requires fine tuning of the standard SEIR model. The way people do is that they split the I compartment into two parallel compartments. I1 and I2. I1 is the asymptomatic people, and I2 is the those who show symptoms. And the rate of interaction, the contacts from I1 to S1 and I1 to S and I2 to S are different, because usually if you are showing symptom, you will be quarantined or something, so the contact is less. But if you're asymptomatic, they'll put a normal contact number, and this can be done. That's the way. In fact, all the models do that. I didn't go into such details, but these things can be done quite easily. In fact, one of the models which this due to this ISR, that India Science Initiative Against COVID or something, that group had 9 compartments actually. It's simply a variant of SEIR, but they have appropriately split the I and E compartments because for it means various things, various phases of disease progression.
So maybe so how well does your model work in sort of predicting or
so that in fact the problem is that one thing one should understand clearly is that if your model is working, then you have some problem, because you are working with a particular alpha and C, right? And your R0 will keep changing. Not alpha and C are one aspect. Second aspect is that you may be, so this washing hands and all, this infectivity rate reduction is completely happening in a heterogeneous manner. So it's alpha reduction. C reduction, okay, lockdown and all, maybe there will be some homogeneity nature. The alpha reduction happening in extremely complex manner, which I don't think any model will be able to capture. So no model should give the actual numbers. That's something one should believe. But then what is the use of all these things? The use of all these things is in giving you relative numbers. Like suppose you have a model, and with a particular alpha and C, you are getting this as the peak value. And after reducing an alpha or C by 1/3, how is your peak coming down? This gives us a policy planner to decide how much you should work on reducing your alpha or reducing your C. And this is this relative justification is the relative calculation of numbers is where the model will help. And that is about the deterministic compartment model. From the stochastic agent model, the way it helps is that that will allow even micro level planning. You can shut down maybe one school and see. In fact, Rajesh tried to do that. Rajesh tried to he collected data from Bangalore Metropolitan BMTC or what do you call it? Bangalore Nagarasabha Palika. And certain region school, if you do try to shut down certain schools in certain regions, how does the SAM differ from the previous SAM? So the difference in numbers will give you some indicators that where you should put the planning on. That is the way model helps. So my model also did not give the exact actual numbers at a later point of time. Initially it was following, but later our numbers.
But maybe would it later have so if you had kept sort of getting fresh data about how
Yes.
updates, would
exactly.
it be so like what kind of error are we talking about? Even in the initial parts.
Initial parts, see, there's another thing is there are various strains people say, right, for this virus, and this incubation period and the recovery period, even those virus specific time constants can be different from the global numbers. So for that we did a survey actually, and we took Kerala specific numbers, and that was different actually. To be honest, the incubation period was actually 2 to 3 days within Kerala, whereas the global numbers were 4 to 5 days. The median was 5.6 or something. So there was a significant difference. So that way, that you can find out from the ground level survey. But after that, your question was intermediately what would change. Intermediately, the contact rate can change. So that could have changed actually. And another important thing is we assume a close population assumption, but after some point Kerala allowed expatriates to come in, and that would have made huge imbalance to this condition. So all these things would have caused us to not predict it correctly at a later point of time.
Biren, I have one question. Can you hear me?
Yes, of course.
Oh, okay. Yeah. So, I mean, I was generally always worried about, let's say you kind of estimate many of these alpha C's and all from the data itself, right?
Yes.
I mean, there are many parameters which are estimated from the data, right?
Yes.
And I mean, the model working and all that, of course, are critically dependent on the parameters.
Yes.
But what I am really concerned about is about the noisiness of the data itself. Because what I kind of see is that whatever data is used to get any parameter is extremely noisy. Maybe
Yes.
not even.
You are right.
So how is that taken into account?
Yes, very good question actually. This is very good actually that asked actually. So there are two things from the ground data that we tried to estimate. One was by doing survey and certain R0 is actually R0 has a physical meaning, as we said. It's a number of infection that you caused, that one infectious person caused over his contacts with others. These things can be actually found out. So the epidemiologists will go to clusters, and so they have something called cluster study, and they will draw the tree diagram for the contacts growth actually, and you can find out. So, and I don't think there will be any unlikely to have errors actually. But another set of data oriented work is to get data from codeindia.org or something like that, large amount of data. The first part which I said is one more point. We actually studied 200 people, very specifically 200 patients and their contact history and all. It's very small amount of data, but in-depth survey is conducted. You will ask the incubation, you will ask them how many people you interact with, and then you looked at those who infected and asked when. So this way, you meticulously you get the information from these people by survey. Second is large amount of data, and you run some algorithm, machine learning algorithm, which is done by Sahil and Bernard. That your question is very valid for the second part actually. In fact, even the people who work in epidemiology trust the first line of work than the second line of work. But luckily for our case, the both, at least the beta values matched in both things, both the things. Maybe it was in the initial time or something. Now I don't know. This was done at least 3 months back. But this in the second line, applying some machine learning algorithms and getting to estimate these parameters, it's very tricky. It can be very tricky. Actually, you cannot trust it at all. I agree to that. So how to handle that noise is another important question. But yeah, we don't know. We don't know.
Birenjith, there's one question from Bibu. If you can see the chat, he's basically asking about when should we change from S0 to S1? Because there is fear of
S0 to some other S1. I didn't. Usually S0 is a constant, but after simulating for certain. No, we don't do that. Yes, yeah. If you're simulating, you don't do that. If you're simulating, you can continue. There's no only S0 will be there, and you keep running the simulation. There's no S1 coming into picture. Okay, maybe let me try to answer in a different way. So, suppose the S0 was used when you want to study the initial growth alone. Okay. Maybe you are asking the question thinking that after some time you will stop this growth, the curve that is causing the growth will be stopped at some point, and then you will find out the S1 at that point, again draw the curve, something like that. But that need not be done, because if you're simulating, you can draw the curve all throughout and get that curve completely. You don't need to stop at some other point and figure out the S1. Hope that answers. Okay.
Yeah, Birenjith, one question about looking at data post facto. So since you have a good understanding of this model, and more importantly, also understand the limitations and the possibilities, imagine you were sitting back after a few months and looking at your model and the actual data. Can you post facto, for example, if there were certain strains that were present up till now or even in future, based on the evolution of the data of the time series, you think you can kind of extract out certain strains kind of causing, because your model would have predicted something. Is it possible to kind of do this analysis now that we're 6 months into the pandemic? For example, you mentioned in Kerala there was a change because, say, the travel restrictions were taken off from the Middle East. But specifically, was
Okay.
it just because of that particular event, or were there big strains in
Yeah.
certain geographical parts of Kerala or other places?
Retrospective.
Yeah, retrospective. I'm just saying later on, I mean.
Yeah, maybe can be done. Of course, there are certain parameters people do after the complete storm is dies down. So, for example, this estimation of R0. So there is estimation of R0 prior, during the epidemic and post-epidemic. There are methods which post-epidemic data will help you, because for a futuristic study, you may need to estimate the R0 and keep, right? So after the epidemic is over, there is a class of methods to estimate RT, dynamics of RT. Whereas the methods, the earlier phase are different actually. So,
so these are both predictive, which are not suitable for saying the post facto analysis of the data. Is that correct? Okay.
No. These are not suitable. There are other methods. So that about R0 I know, but for other parameters I don't know actually.
Okay.
That may be there. Yeah.
Any other questions? Okay, so if not, I guess we can thank Birenjith for an excellent talk. Right, so
Virtual clap.
yeah, virtual claps.
So
Yeah.
thanks for inviting me to this.
Amit, do you want to stop the recording?
Yeah, I'll do that.